So let us take a few questions in data structure and algorithm with answers. So what is an algorithm and what are the characteristics of a good algorithm? So algorithm is a step-by-step procedure for accomplishing some task. Step-by-step procedure to accomplish some task. So an algorithm can be written or given or presented in many ways. For instance, it can be written in English, say French, or any other natural language. But we are interested in algorithms which have been precisely defined using an appropriate mathematical formalism, such as programming language. So every algorithm, because we have been asked what are the characteristics of good algorithm, every algorithm should have these 5 characteristics: input, output, definiteness, effectiveness, and termination. That means input means the algorithm should take 0 or more input. Output means the algorithm should produce 1 or more outputs. Definiteness means each and every step of algorithm should be defined unambiguously. And effectiveness, a human should be able to calculate the values involved in the procedure of the algorithm using paper and pencil. Effectiveness. Termination, the algorithm must terminate after finite number of steps. Next is, how do you find the complexity of an algorithm? What is the relation between the time and space complexities of the algorithm? Justify your answer. Complexity means the space and time complexity. So complexity of the algorithm, the complexity is computed in terms of time and space. So complexity of algorithm is a measure of analysis of algorithm. When you do analysis, see, you have written algorithm. Now you do, or you are performing some analysis. So this analysis of algorithm is the complexity. So analyzing an algorithm means predicting that resources that the algorithm would require, such as memory, it can require communication bandwidth, logic gates, and time. And most often it is computational time that is measured, which is the time complexity. For finding the suitability of algorithm, you may have one algorithm, you may have another algorithm. Both may be able to solve your problem, but the computational time will allow us or will make us decide which to take. This is known as the time complexity of the algorithm. So the running time of program is described as the function of the size of its input. That is why we call it order. So now that is the we have order, omega, theta, etc. So on a particular input, it is traditionally measured as the number of primitive operations or steps executed. You'll see the for loops, a number of for loops which we have data is dependent inside. So depending upon the key operations, we decide the time. So the analysis of algorithm is focused on 2 things: space complexity and time complexity. So as compared to this time analysis, the analysis of space requirement for an algorithm is quite easy, but whenever necessary, both are used. The space is referred to as the storage required in addition to the space required for storing the input data. This space complexity is not that space which is required to store the input data, but it is while the program is running, how much more resources or storage is needed for the program. So the amount of memory needed by a program to run to completion is referred to as the space complexity. So for an algorithm, time complexity depends on the size of the inputs. As we said, that it is the order of growth with the number of input element. So it is a function of size n, input size n, and the number of data elements. So the amount of time needed by an algorithm to run to its completion is referred to as time complexity. So amount of time needed by an algorithm is time complexity. The best algorithm to solve a given problem is one that requires less memory. That is, space complexity should be less and take less time to complete its execution. That means the time complexity also should be best. But what happens in practice? It is both of them. It may be possible you can get it. It may not be possible, and because we have more than one approach to solve certain problem. So the best is to choose that algorithm where the running time is the best or the least, and the space is also the least. Okay? So we have to some trade-off or compromise between the space and this performance, time and space complexity somewhat. We have 2 functions, n square and 2 to the power n by 4, or value of n, determine when second becomes larger than first. Let me tell you that n square and 2 to the power n. If you see the precedence order, first is what? First is the constant time. Then we have log n, then n log n. So it increases up to 2 to the power n. So 2 to the power n is the highest. Means the time complexity is highest here. Means it is exponential. So let us compare these two with respect to n. So as we see that we pass n here, so it will be n square to the power n by 4. That is 2 to the power 1 by 4. 1 by 4, that is 0.5, that is half. Then we start putting the values up till 10. And we see that n equal to 8. At n equal to 8, they both are same, 64, 64. Right? But after this is increasing. For input 10, n square was 100. But the 2 to the power n became 256. But these are very, very less numbers. We are not interested in this. We are interested in 10 to the power 9, 10 to the power 10, 10 to the power say 20. For these type of numbers we are interested in. And this n square is definitely going to have an edge. Explain an efficient way of storing a sparse matrix in memory. Write a module to find the transpose of a sparse matrix stored in this way. What is exactly sparse matrix? First understand that. A matrix in which number of zero entries are much higher than the number of non-zero entries, we know or we term it as a sparse matrix. So a natural method of representing matrices in memory as 2D may not be suitable for sparse matrix because there are a number of zeros. So one may save space just by storing only non-zero entries. For example, if this is a matrix which can be written in sparse metric form as what? These are our values 2, 5, 6, 9. So where 2, 5, 6, 9 have gone? Here 2, 5, 6, 9, all these values are there. So we have one number of where this first row is, let me tell you, one more is there. So this first row represents the dimension of the matrix. Last column, it represents the number of non-zero values. How many non-zero values? We have 1, 2, 3, 4. 4 non-zero values. Okay. Second row onwards, it is giving the position and the value of non-zero numbers, which are the second for next one. So it is giving the position, but we are interested in that we have 4 non-zero numbers. The first row, as here, represent the dimension of the matrix because this is 3 by 3 matrix. So we have 3 by 3 matrix. So it is 3, 3, 3 by 3, and now 4 non-zeros. So this is how we can easily represent, and we are just pointing out the positions also. Where is 2 at 0, 1? Where is 5 at 1, 0? Where is 6 at 2, 2? 2, 2 is this 6 is the second row and second column. Here 9 is where? Third row, second row, third row. It should be third row, third column. Okay. So this is how the positions can be told, and this is how we can efficiently store the sparse matrix. Write a module to find the transpose of sparse matrix. So this is the module to transpose the sparse matrix. And in this, what we have done is we have taken the x, y, and r. X is a matrix 3 by 3, y is a matrix, and then the transpose is just changing the row to column, which is what we have started here. If t equal to greater than 0, then for all columns and rows, if you are well versed with programming, if then you are aware what is happening. But the main thing is we are just trying to change the first, second, and third. These are the transposing values we are doing, and every time we are increasing the value. This is the simple transpose of sparse matrix. Then explain an efficient way of storing two symmetric matrices of the same order in memory. Symmetric matrices, efficient way of storing two symmetric matrices of the same order in memory. So a n square matrix array is said to be symmetric if AJK is equal to AKJ for all J and K. Okay. If AJK equal to AKJ for any n square matrix, we say it to be a symmetric matrix. For a symmetric matrix, we need to store elements which lie on or below the diagonal, or those on and above the diagonal. So the two symmetric matrices A and B of same dimension can be stored in an n into n plus 1 array. Say C, where you see that CJK is equal to AJK, where this J and K, we see that this explanation or this assignment is nothing but Cjk, Ajk. And we are talking about Cjk, Jk minus 1 is equal to Bjk minus 1, where J is less than K. Where J is less than K, and when J equal to K, we say J is greater than K, this should hold. And when J is less than K, this should hold. So for if you are not able to understand, let me tell you that this is a efficient way of storing two symmetric matrices of the same order. So what we have done is, we have A11, A21, A31, and B22, B11, B22. So this is the form we can, applying these two, we can store two symmetric matrices, which follow that Ajk should be Akj. Now write an algorithm to evaluate a postfix expression. Execute your algorithm using the following postfix expression as your input. So this is the algorithm to evaluate the postfix expression, and this is how it is done. Let me show you with an example first, then we'll come back here. We have AB plus CD plus into F then cap. Okay. So in stack, first what we are going to do, we are going to place the first one which will come. So we place on stack A. Then the second operand will come. So we'll also place it in the stack. So we'll do a push AB. Now the plus will come. So as soon as a plus will come, we will pop A and B. So we are going to pop A and B, and then evaluating A and B and plus, that is A plus B, we are going to evaluate, and then we push A plus B onto the top. So that will be A plus B and then C. Okay. This A plus B we have pushed, and now C has come, so C will also be pushed. Then D has come, this D has come, so D will also be pushed. Then plus has come, so C and D will be popped, and a plus, that is the addition operation, will be applied on this CD. So CD, so finally what will happen, A plus B was there already, C and D were popped and then added, and then the result was being placed there. So ultimately we have C plus D, A plus B and C plus D in this case. So stack is containing A plus B and C plus D. After that what happens, that there is a multiplication sign, there is another operator. So what we are going to do, we know that this result we have already pushed, and then after that we have pushed this result. So these two will be popped, and this operation will be done on these two, and the final result will be again pushed here on the stack. Then the F has come, so F will go ahead, then we will push the F on the stack, and then this operation has come, so we'll pop this and F, we'll apply this, and finally this is the expression. So the result of the evaluation is this: A plus B first into C plus D, then cap, and then F. So we first clear the stack, and then we input, the symbol will be the next input character, and while the input has not ended, we have not reached here, if there is symbol, if the symbol is an operand, we push onto the stack. So if A, B, C, D has come, we have already pushed them onto the stack. Otherwise, we pop two operands from the stack, as we have done. We have popped A and B, then we have popped C and D, and then we apply the symbol between these operators, and we push this result onto the stack. And then the next input character will be the symbol, and the result final will be the pop stack, that is the topmost after this completion. What are circular queues? So what are circular queues? Let us see. Circular queue, see, static queue have a drawback that once it is full, even though we delete few elements from the front, and relieve some occupied space, we are not able to add any more elements at the rear. As the rear is already has reached the queue's rearmost position, so it is already full. You want to delete elements from here, you have space here, but still you cannot utilize it. So the solution lies in the this thought that in a queue, with the moment this rear reaches its end, the first element will become the queue's. This first element will become the queue's new rear. So this will be the rear. So this type of queue is known as the circular queue, having a structure like this which once the queue is full, the first element of the queue becomes the rear element, if and only if the front has moved forward. Okay. Now, given a set of input representing the nodes of a binary tree, write a non-recursive algorithm that must be able to output the 3 traversal orders. Write an algorithm for checking validity of the input. That is, the program must know if the input is disjoint, duplicated, and has a loop. So this is the explanation for the pre-order reversal or traversal. We are provided a set of nodes. So you give a set of input representing the nodes of a binary tree. So you have to write a non-recursive algorithm that must be able to output the 3 traversal orders. 3 traversal are pre-order, in-order, and post-order. So the process of doing pre-order traversal iteratively will have these following step, and we assume that a stack is available to hold pointers to the appropriate nodes. So we push null onto the stack. Then we start at the root and begin execution and write the information in the node. If the pointer to the right is not null, we push the pointer onto the stack, this one. Okay, say right. If the pointer to the left is not null, we move the pointer to the node on the left. Okay? On the left, and if the pointer to the left is null, we pop the stack. And we repeat these 3 to 7 until no node remains. Okay? Then this is the same for in order, and there is as we are going, how we do the traversal in a binary tree. This is a binary tree. I'm taking just 3 nodes. So in the pre-order, in the in-order, and in the post-order. So in the pre-order, what we do, first let me tell you the in-order. This is the basic one. So we take the left one, then the middle, and then the right. So only the position in which we take the root is changed. In the pre-order, we take first the root, then these two. In order, we first take this, then root, then this one. And in post-order, we first take these two, then the root. So this is the explanation and the algorithm. The next question is, what is BST, a binary search tree? Make a BST for the following sequence. And traverse the tree in pre-order, in-order, and post-order. So binary search tree is something like this. A binary tree is essentially a binary tree only, which satisfies a certain condition that the left subchild, a left tree, all the members should be less than the root, and all the members on the right should be greater than or equal to this root. And this left and right, these subtree, they again should be binary search tree. These are the pre-order, in-order, and post-order traversal of the these are the nodes in which every tree has a left subchild, right subchild, and a root. So pre-order is first we take the root, then left, then R. In order, we take first left, then root, and then right. In post-order, we take left first, right after, and then root. So let me take in order for you so that you will be able to do the pre-order and post-order. So what we are going to do here is we'll start with 45. And we know that first we have to take the root, then the left, and then right. In order, because we have come here and this is the root. It has a left subchild and right subchild. So first we will take the root one because we have to take the root first, 45. Then we come to the left subchild. In this we have this root, this is the left subchild, and this is the right subchild, or you can say right tree. So we'll take 36. Then what we have to do is we have to take the left 23. It has no null node, so we'll take 23. Then we go to the right. And this side, this is again a tree. This is again a tree with null here. So we'll take the root first, 39. There is no left, so we'll take right only, 41. Okay, this is done. We come to the right subchild. That is the right subtree actually. Now what we have to take is, first of all, we have to take the root, 76. So we take the root. Then we go to the left. Again we have a tree. Again we'll take the root first, 56. Then go to left, 48. Then go to right, 69. Now root is over, left is over. We go to the right. In this, we already have because this is a tree, so it has null here, and right it has another tree. So we'll take the 89 first, nothing here, then 89 will write. Then we come to this right last subtree. What we have to do is first we have to take the root, then the left, that is 98, and there is no right subtree. So this is the in-order traversal of this tree. I will encourage you to do this pre-order and post-order by yourself. What are the expression tree? Represent the following expression using a tree. Comment on the result that you get when this tree is traversed in pre-order, in-order and post-order. So this is a tree. You see this is an expression. So it will give a result, something. One value will come. So we'll try to make a expression tree. This is the expression tree for this expression. So the leaves of an expression tree, these are operands always, such as constants. These are constants of variable name. And the other nodes which you see here, these will contain the operators. So these are operators. So this particular tree happens to be a binary tree because all the operations are binary. And although this is the simplest case, it is possible for node to have more than 2 children also. So it is also possible to node to have only one child, as is the case with the unary minus operator. You also have a unary operators. So we can evaluate this expression by applying the operator at the root to the values obtained by recursively evaluating the left and right subtrees, like this. So this expression is a minus b divided by c into d plus e, and these both expressions are divided. So the traversal will be, we have just shown the traversal. So we have taken the in order in the previous case, this example. So let us take a different one so that you understand it better. Let us take the pre-order first, this time. In pre-order, what we do, we take the, because we have brackets also, so let us start with the bracket. But in this pre-order and in order or post-order, in these traversals, we follow certain rules. That is, prefix notation will come, postfix, that is also known as, postfix is also known as reverse Polish, prefix is known as Polish notation. So as last time we took the in order, this time we'll take the pre-order, this one. In pre-order, what happens? We take root first, then left, then right subtree. Let us take the root first, that is divide. So we transfer it here. This is the first one. Then we go to the left. In left we have again a and b. So we know that we have to take the root first, root LR. Root we have taken minus and then LR, a and b. Then we come to the right subtree. Here we have to take first of all the root. So we take the plus. Okay. Then we take the left one. In this left, again left we have to do in pre-order only. So in left, first we have to take this into, then C and D. And as we have taken plus already, we have to go to the right, that is P only. So this is the pre-order terms. I hope you will be able to do in order and post order by yourself. How do you rotate a binary tree? Explain the right and left rotation with the help of an example. Rotate a binary tree. Rotation in binary tree. If after inserting a node in a binary search tree, it should be binary search tree actually. The balancing factor, the height of left subtree and minus the height of right subtree. This is the balancing factor. Height of left subtree minus height of right subtree. So this is the balancing factor. So the balancing factor of each node remains 0, 1 and minus 1. There is no need of modification to the original tree. That will be all fine. But if the balancing factor of any node is either plus minus 2, that is either 2 or minus 2. We also know this tree, something in the name of avian tree. So the tree become unbalanced. So it can be balanced by using left and right rotation or combination of both. Let us consider this tree. In this tree, this is now, see the difference of left and right subtree. This is 0 because no left right 0. Here no left right, but here left is 0. Okay, left is 0. The left and right subtree height is minus 1 because for this is 0, for this is 1. So 0 minus 1 is minus 1. So it has height factor of minus 1. No problem with that. Here also this is 1 and this is 2. So 1 minus 2 is minus 1. So this is minus 1. But in this case, this tree, this is 0 and this is 1, 2, 3. So 3, 1. This is 0 and this is 1, 2. So 0 minus 2, that will be minus 2. So now as we add this 70, otherwise it is fine, balanced. But as we enter or add 70 here, what is happening? That this tree has now become -2. Though it was fine earlier, this was fine, but adding 72 or trying to insert 70 will unbalance this tree. So what we are going to do is, the balance factor of tree of node 2, this has become 2, so the tree is rotated left to have a height balance tree. So what we'll do here is, we have to balance it. So 60 goes up, 35 goes down, 20, 45 comes here, this one comes here, 45 come here, 60, 65, this 65, 70 remains like this only, because they are connected to 40, but 45 has to move here. So now if you compute the height of left subtree and height of right subtree, this remain 0, -1 or 1. So this is how it is done. In the similar case, this is a tree. Now you want to insert, this is okay. But as you insert 10, if you remove this, see, this is balanced. All these are balanced. But as we go here, the difference becomes 2. Because 1, 2 and 0. So this will be 3 minus 1, that will be 2. It will become 2. This is unbalanced. So we have to do a right rotate line. How to rotate? 30 will take this place. We are rotating it, right? 35 will go down. And this one, because it has gone up, what to do with this right subtree? It will come or will be connected with 235. And others will be the same. They'll take their position. So this is rotate line, right? Right. Taking a suitable example, explain how a general tree can be represented as a binary tree. How a general tree can be represented as a binary tree. So how we can convert a general tree? This is a some general tree. So a general tree can be converted into its equivalent binary tree. So this conversion process is called the natural correspondence between general and binary tree. So what is the algorithm? We insert edges connected siblings from left to right at each level. Left to right at each level. We delete all edges of a parent to its children except its leftmost offspring. We rotate the resultant 45 degree to make clearly left and right subtree. So the general tree, which is in figure A, this can be converted into the binary tree as shown here. What we have done is, we inserted edges connecting the siblings from left to right at the same level. So see, what are on the same level? B is on the same level, because after A, this is B, then C, then H, I, J. Oh no, D. So B, C, D, they are on the same level. So B, C, D are, we insert the edges connecting siblings from left to right. So B, C, D are siblings, so we have done this. After that, we have E, F, and then G and H, I, J at same level. So E, F, G, H, I, J at same level. Right? And then K and L, they are at same level. So K and L at same level. And we delete all edges of a parent to its children except to its leftmost offspring. So we took this, but we did this deletion, so ultimately we got this right one. And whenever it is required, we rotate the resultant tree 45 degree. So when we rotate it 45 degree, the result will be like this. This is how we convert a general tree into a binary tree. So this is all for today. We'll be taking more of these questions in later session. Thank you so much.